Hello, you wonderful earth science kids. This is Mr. Johansson here. I just want to talk briefly about the electromagnetic spectrum and our reference table version of it. And then I'm going to bring it into the greenhouse effect a little bit, so you'll have a better understanding of how that works. So we have different categories of electromagnetic waves. And basically we have a charged particle vibrating. That's all that it is. It makes an electromagnetic wave. If it's not vibrating very fast, imagine a cork floating in water, and as that cork starts vibrating faster and faster and faster, imagine the waves that are going to come off of it. Well, the longest waves represent the least energy. Those would be radio waves. As we increase the energy, increase how fast it's vibrating, we decrease the wavelength. So as it starts vibrating faster, we go from radio waves into microwaves. Now we use waves to communicate by radio. When you tune your radio set into something like your favorite radio station, you're listening to radio waves. These are still a form of light, however. When you're listening to a radio station from New York City and they say it's 12 o'clock noon, was that 8 minutes ago or something? Was that this long period of time ago that it took a sound wave to get to you? No, it's now. It travels at the speed of light. So it took an infinitely small, or a nearly infinitely small time to get to you. Your phone uses microwaves to communicate. Your microwave cooker uses microwaves to cook food, for reasons you can learn about in physics. As you start vibrating faster and faster, eventually you get into the infrared energy. Now, infrared is starting to get close to the light that you can see. But more than that, your skin can sense infrared energy. You feel it as heat. When you go outside in the sunlight, you feel the infrared energy raining down on you from the sun. As we increase energy, we enter this special place, and it's special just because of you and me. We can see this. So when I start vibrating, the first time, even though I'm still at low energy, I'm vibrating fast enough to be able to see, is red. So that would be the lowest energy vibration that I still could see. Imagine taking a piece of iron and putting it in a foundry and getting it hotter and hotter and hotter in the blast furnace. The first color you'd see when you take it out, that your eyes would be able to see, is this deep red color way down here. And as you got it hotter and hotter, the color would increase to orange. Hotter would increase to yellow. You would never see green, because by the time you get to green, all these other colors are still there, because some atoms are still vibrating that fast. So you would then get more or less white light, and as you got into blue and violet, it would just get whiter, maybe a bluish tinge to it. In any case, if you start vibrating even faster, making shorter vibrations, now you're in the ultraviolet spectrum. These are very short, and the shorter they are, of course, the more energy they carry. Ultraviolet light carries enough energy that it can penetrate your skin and hit your cells there and hurt them, some of them even turning cancerous. That's why ultraviolet light is dangerous for you. But of course, if you think ultraviolet light is dangerous for you, how you feel about X-rays? Well, we know X-rays can go right through you. We can take pictures of you using X-rays. We also know you don't want a bunch of pictures of you in X-rays because they're not really very good for you. They can detect if you have a problem, but we would like to use the least amount of them possible. And if X-rays are not so good for you, you know these, the gamma rays, would be really, truly bad for you. And we don't do a lot with gamma rays here on the ground, but in astronomy, whoa, there are things that happen that give off gamma rays, and they are impressive things that happen. So this is the electromagnetic spectrum. Now let's talk about how a greenhouse works, and I'm using this really to represent the atmosphere. It's amusing that a greenhouse really doesn't exactly work this way. But if you look at light going through glass, there's a particular wavelength. So let's just say this is the wavelength of light. And when you look at light, going through glass, well, does glass interrupt it? No, it goes right through glass. That's why glass is transparent. So this light continues down, and I'm going to put a surface here just so I don't have to get all the way down, and it hits the surface here. And what does it do to the surface here? Well, the surface gets hot. Now, where's this light coming from? Where does this light come from? This light comes from the sun. Let me ask you, which is hotter, the sun or this board heated up by the sunlight? I think you would agree with me, the sun is hotter. That means the sun is vibrating much, 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 much faster, making visible light. So this is visible light. And it's visible because the atoms on the sun that are giving it off are vibrating so fast because they're so hot. Is this board as hot? No, it's hot, but it's not anywhere near as hot as the sun. So the atoms aren't vibrating as fast as the sun. Atoms on the sun would be vibrating. So these atoms then are giving off much longer waves. Now, can you see them with your eye? Does the board glow? No, it has reflected light, but it doesn't glow on its own that your eyes can see. But if I had an infrared detector, I would be able to see it because these rays are infrared, right? And infrared waves are carrying the heat. But funny thing about them, while this glass lets visible light through, glass doesn't let the infrared light through. Glass reflects the infrared light. So the greenhouse gets warmer. This is exactly analogous to the Earth's atmosphere. The sunlight in short waves comes down, hits the ground gets hot, and it gives off long wave radiation. We call this infrared radiation terrestrial. Why terrestrial radiation? Yeah, you got it, because the Earth is a terrestrial planet. Terrestrial just means land. So this terrestrial radiation goes off and bounces off, or actually is absorbed and re-radiated by things in the air. What are some gases that absorb it? Well, the most common one is water vapor. What's another gas that absorbs it? You got it, CO2, and that's one of the gases we have trouble with. What's another gas that absorbs and radiates it? Methane. So these gases absorb the infrared radiation. Visible light, shoo, goes right through them. But infrared radiation is long enough wavelength that these molecules can absorb them and send them back our way. So that's a little bit about how the electromagnetic spectrum and greenhouse effect work together. I always wondered, if visible light can go right through glass, how come infrared can't go through? But when you think of just an entirely different size wavelength, it makes a lot of sense. And that's all there is to it. So infrared radiation is very long wave radiation. Visible or ultraviolet radiation is very short wave. And if that's visible light, then ultraviolet light would be even shorter wave, right? And what absorbs the ultraviolet light as it's trying to come down to us? Ozone absorbs the UV and sends it packing, all right? Hey, thanks for watching this episode.